so we keep investigating M star, checking to see that it has properties that we would intuitively regard as a measure of real numbers. To summarize, we have already checked that it gets intervals right and that it is translation invariant, so far so good. One other property that we discussed a while ago is this sort of additivity property, right? That if you had two disjoint sets, then you should be able to figure out the measure of their union by just adding the measures of their pieces, right? So it's one thing for this to hold for a finite set, right? Here it's just 2, and if it holds for any 2, then it's easy to show by induction that it holds for any finite number of unioned sets, right? Disjoint, all of them disjoint. But what we would really like is a slightly stronger, well, not even slightly stronger, a significantly stronger condition that that it be countably additive, right? So you know, more than just for 2 sets, more than just for any finite number of sets, but for any countable collection of sets, we would like additivity to hold. So we will investigate whether or not M star is countably additive. So naturally, right, as we often do in analysis, in order to try to prove an equality, we approach it by proving less than or equal to and then also greater than or equal to. So if we focus on this less than or equal to, then this has a name, right? If under basically the same conditions, right? So you've got any set, you've got a subset of the power set. By the way, this is all stated so that later on, when our x is no longer the real numbers, we can sort of generalize to a more general measure space is what we'll call it eventually. But in any case, so this is set a little bit general in order for later on when we generalize. But so we have any set, any subset of the power set, function from that into the non-negative extended real numbers. So under those same conditions, now this time we only require that we have a sequence of subsets of the set S, right, the subset of the power set. They are no longer, for this direction, they are actually no longer required to be disjoint. And that's because we can prove, right, like, so if it's true for anything, it's also true for the disjoint one. So we kind of, the fact that we can do this without using the disjointness assumption is sort of worth emphasizing here. So they don't need to be disjoint. This result actually still holds. And when it does, we call it countably sub-additive. Theorem, our M star is countably sub-additive. Okay, so we'll get started with the proof that M star is countably sub-additive. And so naturally, we will just take any countable collection of subsets of the real numbers and argue this inequation. Quickly note that if any one of these terms is infinity, then there's nothing to prove because the inequality turns into infinity and becomes trivial. So we assume that every single one of the sets has finite measure. Now, the basic strategy behind this proof is going to be that we'll take any one of these sets and associate it with an open interval cover. By definition of the infimum, if you add a little bit, then there must exist some element of the set that is underneath it, right? So I'm going very fast here because I really just want to motivate that we are going to need a little bit of a sidetracked proof of some lemma in order to get back to this proof. So I'm not really doing the proof right now. I'm just quickly trying to convince you that we will need a lemma. So what lemma do we need? Well, so notice for each fixed j, right, pick a set It's associated with a collection of open intervals indexed by k, and by definition of the infimum, if you add a little bit, then there is something in the set which is underneath that, which is namely this sum over k of these intervals. Now, so far, nothing is terribly problematic there, but we will, right, it'll be fairly easy to relate this set to this sum, or sorry, this number to this sum. And it's this move right here, right, saying that if you sum over all possible choices of j and k, that it's the same as, right, there's going to be like an equality here, and then you replace this with the sum over the k's. But the point is, when you go from here to there, you need to know that summing over all possible j and k is the same thing as first summing over, like summing over the j's on the outside and summing over the k's on the inside. Now, this is a very strong rearrangement of the terms, right? If you've seen real analysis, you should be familiar with the fact that if a series converges absolutely, then you can permute the terms in any way that you want. But that's a singly indexed, sum, which, is not exactly what we're looking at here. So that doesn't quite do the trick for us. Now, you also may have seen that if you have a double sum doing j first, then k, it's the same as if you did k first and then j. But that's also not what we're doing, right? Like, that's what this is. This is j first and then k. But this is jk, right? All possible jk with no specification of the order, so that, in some sense, this is saying that you would index all of the intervals by some enumeration, right? Like, kind of like having a singly indexed enumeration of these indices and summing over that single index base, right? Like, that's kind of equivalent to what this is saying. So we need that, right? We need a bridge between a double sum and a single sum which is enumerating all the terms in the double sum. That's a stronger rearrangement theorem than you tend to encounter in real analysis. Now, this is a bit of a lark, right? This is not really that important to the current topic. So you would only really get hung up, right? Like, you can just be, assured that the equality is true because all the terms are non-negative, right? And if that's enough for you, then absolutely just take that for granted and skip the next theorem and proof, right? This lemma that I'm about to get myself into. It's long and a little bit complicated, so it makes a lot of sense to skip what I'm about to do. But if you really like to know that you can handle the proof of this fact, if you find that to be important, then we're about to do it. Okay, so we will prove what I am going to call the total rearrangement theorem, and basically the reason for calling it that is that if you are already, and hopefully you are already equipped with the theorem that absolutely convergent sums can be permuted and it does not change their value, and that double sums can swap, then if you put that together with this, really you only need the first one, if you have all of that, then if you then further have this theorem, then that's kind of the most complete sense in which it doesn't matter what the order of the terms are. So the statement of the theorem is going to be that if you have any double sequence of real numbers And they converge absolutely. Keep in mind that the double sum converging absolutely means that for any fixed k, this is some finite real number, and the sum over those, right? Like so once you've summed over k, this is then a single term indexed by j, and if you sum all the terms indexed by j, that sum also converges. If we then also enumerate all of the terms, and this is just due to the fact that a countable union of countable sets is countable, right? So we know that if you fix j, you get a countable collection indexed by k, and there is a countable number of indices labeled by j. So when you put all the terms together, that's a countable union over a countable set, over countable sets. And so therefore it is countable, and so let's take this to be any enumeration of that set of terms. Then, under these assumptions, the double sum is equal to the single sum over the enumeration. Okay, so how do we prove this? Well, effectively the strategy is going to be to look at growing sequences of boxes, right? And because we sort of index the boxes by a single index, right? So like, S1 will just, or S11 will be just this single term at the start, but then S22 is going to be this one, and S33, right? You just get these growing boxes that, right, if you keep the index the same in both coordinates, then it's a single index grabbing all of these terms. And so that'll be one enumeration, right? Like that's at least one sum that is going to be equal. And so then if you take the sort of the equality of the double sum, right? Keep in mind the double sum first fixes a row and sums over all the columns, then fixes the next row, sums over its columns, and so on, and sums all those results together, right? So this is one particular sequence of summing over the double sequence. This is going sort of row-wise. If that's the same thing as having a single index indexing the boxes, then you can rearrange the, right, you can use your earlier theorems at that point to rearrange the terms in that singly indexed sequence, so that effectively any order of summation is equivalent under these assumptions. So we define S sub mn to be any rectangle, right? Notice that S sub mn is going to be the sum over all the terms in the rectangle, where the bottom right element of the rectangle is the same as the indices of S sub mn, right? So S sub 24 is the sum over all of these terms, and its lower right term in the rectangle is A sub 24. Okay. Now, because this is a nice and general theorem, which is more than just about non-negative terms, but it has these absolutely convergent terms, then this makes some intuitive sense that we might want to have some language to help us talk about this kind of a thing. So we also define a T sub mn to be exactly the same thing, but where we're just taking the absolute values of the terms, right? So if you just kind of put absolute values over every single one of the elements in this grid, then you could make basically the same picture to visualize T sub mn. And again, we'll be looking at sort of restricting T sub mn to just taking growing squares so that you have a single index n just by enforcing that both of these indices are the same. And, just to get started, let's make sure that we can confirm that the limit, by the way, and that's a valuable point, is that when we talk about this convergence of a singly indexed sequence, we're talking about the limit of S sub nn as n goes to infinity, right? That's the thing that we're going to show is equal to the double sum, just to get started, right? And then we'll sort of finish it off with making the case that, you know, rearrangements of those terms also converge to the same thing. But anyway, so so we want to know that just to get started, right, just to be able to sort of talk about this thing, we'd like to know that this limit converges as n goes to infinity. And that's a relatively simple one because all the terms are non-negative, therefore it is an increasing sequence, right? Each next n, you know, getting bigger and bigger squares, just adds non-negative terms. So it's an increasing sequence. A very simple proof shows that it is bounded above by this thing that we assume is a finite real number. Right, this just goes by saying, well, look, I've got this infinite, or I've got this sum over n terms, each one of them, you know, is made up of non-negative numbers. So, like, if so this is also for a fixed j. This is an increasing sequence. So, if you take the limit as that n goes to infinity, you get a potentially bigger quantity. And by the same sort of argument, if you now take these terms, which are non-negative, and let the limit as, ooh, that should be an m. If you let that m go to infinity, then again, it is a potentially larger quantity. So it's bounded above increasing. So by the monotone convergence theorem, the limit as n goes to infinity exists. Okay, so a lot of that kind of, you know, does some minimal work just to make sure that certain things exist. We'll do maybe slightly less minimal work, but still all we're going to do is show that this limit exists, right? So still not really, you know, we're basically just guaranteeing that things exist before we prove that they have the properties we claim they have. But anyway. So to show that this sequence exists, right, lim n to infinity of s and n, well, you know, we'll try to, you know, just show the Cauchy condition, right, that like the mth term minus the nth term is less than epsilon if we pick m and n big enough. And in order to prove that, right, in order to construct the big N which makes these terms big enough, well, you know, if you don't know what else to do, let's draw a picture, right? So what does this absolute difference look like in terms of this grid? Well, if I just kind of summarize every term by a dot, then especially if we impose the ordering that m is greater than or equal to n, then Sm is all of these terms, and mm is these terms, nn is these terms. And when you take the difference between them, basically all the terms of the smaller one cancel, leaving this kind of, you know, backwards L. And we can basically, you know, sort of decompose this backwards L shape into the part that's above here, right, this small rectangle up here, and this longer rectangle on the bottom. So let's see if that gets us anything. Okay, so if we look at, again, we're talking about this thing, trying to see that it becomes smaller than any chosen epsilon for some choice of n large enough. So looking at this thing, and using the insight, it becomes this, right? If you think about the index running from 1 to n, right, that's the rows. So this is summing over the rows from 1 to n, but only the columns from n plus 1 to m. So this right here represents this little top portion of what remains after cancellation. Plus, right, that's an important switch, right? I mean, especially because this is going to turn into a plus, then that means that if and when we use the triangle inequality will be a nicer approximation on a plus than it tends to be on a minus. So that's a nice change. And then here, our starting index is n plus 1. So all the way down here to m, down to here. So it's the latter rows, but summing over all of the columns from 1 to m. Okay, triangle inequality twice or so. And now notice that because we are summing over the absolute values of the terms, that just is these t's, right? In fact, you know, what you should kind of back rationalize about this is that we probably only defined and cared about the t's because, you know, right, if you were really doing this from scratch, you would sort of like start here, get to this, try to figure out what to do with this, and maybe recognize that, well, it's basically the exact same grid, but with the absolute values on the terms, and maybe that's how we ever discovered that the t's matter and that this is a sufficient condition for the theorem. But anyway, so this is just exactly the same grid, but with absolute values on all of our terms. So it is exactly the same thing as if you took t sub mm minus t sub nn. And from the fact that the t's converge, we know that this can be made less than epsilon for some choice of n, right? Blah, 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 based on what we know about the limit of the t's converging. So there you have it, right? I'm not even going to write out all the rest and the details, but that basically convinces us that for large enough m and n, this becomes small. Okay. Okay, so we are now justified in saying that the limit as n goes to infinity of the Sn n's is equal to s, which is some finite real number, right? Non-negative, but whatever. Anyway, so we now want to show that s, that limit, is equal to the double sum, right? Taking j first and then k. And so we'd like to show that this becomes arbitrarily small. Notice that this doesn't, right, this is an infinite sum, right? This is j from 1 to infinity, k from 1 to infinity. So there are no indices in this. So we just want to show that in general, for each choice of epsilon, this can be made smaller than epsilon. It is enough if we can show that it is true for this, right? Because after all, if you, right, if it is true for every possible choice of fixing an upper bound on the first sum, then you can take the limit as m goes to infinity, right? M is then like a parameter over here, but it's not over there. You take the limit. Okay, fine, you don't keep your less than, you get a less than or equal to, but I'm not going to, you know, sort of quibble over tiny details like that. So it suffices to show this, and by a similar kind of logic, to get that, it suffices if we could show that this holds for every fixed m and n. So right then you take the limit as n goes to infinity, and then you take the limit as m goes to infinity. So how could we show, and by the way, notice that this double sum going to m and then to n is the same as the little s sub mn, right? That's just a rectangle of m rows, n columns. A fairly, right, like, I mean, you know, you've probably done this a million times if you took real analysis, which is that you sort of wiggle in a little bridge term, right? So a nice natural bridge term here would be s sub mm. Why? Well, I mean, it seems simpler than mn. And after all, you know, what you always do when you wiggle in this bridge term is you use the triangle inequality. And this part of the result from the triangle inequality, just by definition, can be made arbitrarily small for a large enough choice of index. So that's fantastic. We know that that's completely manageable. So what about this one? Well, that's the trouble spot, but you know, but it can be dealt with, of course. So to get bounds on this term, we do the same little sort of rectangle trick, right? Draw the diagram, convince yourself that the difference between these is just, a sort of a rectangle canceling with a square, and it leaves a smaller rectangle, which, is equivalent to the sum over these terms. Triangle inequality, triangle inequality. Identify that as the same rectangle in the grid of absolute values of terms. Now, what do we do with that? It's a lot less clear than it has been in other cases. What you'd like is you'd like to sort of like, know that like here this is like looks really close to the limit. If you took the limit and, being intuitively kind of like an increasing sequence, then if you subtract a little off of the limit, blah, 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 maybe the easiest way is just to say, well, look, we've already proved that the set of terms is bounded above by this limit, and therefore, right, and it's an increasing sequence, so it has a supremum, and if we subtract from, right, the supremum is just a little bit easier, a little bit more immediate to say, look, if we take that thing, subtract off of it, then just by definition, there has to exist some term in the sequence, and this is increasing in both the first and second index, so easy enough to show that if you just selected the max between them, then no matter what terms you pick above the max, it will only be bigger than this one, but stay smaller than that one by definition. So you get this sort of system of inequalities. And then that allows you to manage this thing, right? So on one side of it, you could round this one up to b. You could round that one down to b minus epsilon and get epsilon. Do a similar thing on the other side, right? Round this down and this up, and you'll get enough to prove this right here, that this thing that we wanted to show becomes arbitrarily small, does become arbitrarily small, and now we are justified in sort of saying, yes, this also becomes arbitrarily small, right? So to make that a little bit more rigorous, not fully rigorous, I'm not trying to, but this can be small as you want by choosing an appropriately large n. This also, possibly by choosing a different n. The usual trick is to take the max between the two n's and you get the result. Okay, to cap it off, let's get back to the enumeration that really began this whole thing. And it's easy enough to show that the sum over any enumeration is less than or equal to this limit of the squares that we just showed is the same as the double sum. So how do we do that? Well, pick any pick any index, right? Go out as far as you like into the sum, and there will always exist a square containing all of those terms, so that this is never, right? This cannot be bigger than that, for instance. Right? So in a sense, every partial sum here is less than or equal to some partial sum here. And it's an increasing sequence. So you get this inequality, and by a similar argument, right? For every possible square, you can go far enough out into the enumeration until every single term in the square is some term in this enumeration, so you get that inequality. And again, because they're increasing sequences, then this inequality follows. So there you have it, right? So the double sum is equal to the square sum is equal to any sum over any enumeration. And effectively, that tells you, right, like, so now, not only have you had this particular double sum, but in fact, you know that this double sum is the same as the square sum, so would any rearrangement of the sums also be equal to the square sum. All of them are equal to any permutation of the terms. All of these things are equal under the given assumptions. So lemma complete, and we can get back to proving sub-additivity.